Welcome at the last 5 final video lectures of the second part of the Solar Energy MOOC on PV technologies. In these final lectures I will review various aspects of the PV technology. The learning objective of these videos are diverse. What are the currently record efficiencies for lab-scale solar cells for the various PV technologies? First, the global installed PV power has been an unprecedented growth in the last 20 years. The cumulative global installed PV power has grown to above the magic border of 1 terawatt. If I assume that an annual installation of 230 gigawatt peak has been achieved in 2022, the total global installed capacity must have been approximately 1180 gigawatt peak at the end of 2022. In 2021, solar electricity was responsible for 3.6% of the total global electricity generation, a contribution that is expected to keep on rapidly growing in the future. Note, the red bars illustrate the amount of global PV power that has been installed annually. These annual installations have been steadily growing as well, indicating that the production capacity for PV modules is still expanding and the annual growth is expected to increase further. These impressive figures have been a result of 3 decades of research and development advances in the various PV technologies discussed in this course. Next, you see the NREL chart with record efficiencies of the various PV devices. Purple corresponds to the 3.5 PV technology, blue corresponds to the crystalline silicon technology, the green colors correspond to the performance of the thin film technologies like cadmium telluride, CIGS and thin film silicon. Among the red colors you will find the PV technologies like organic PV and the perovskite PV technology. The advances in all these technologies are going really fast. Record after record is being reported. Therefore, I have to warn you that some of the efficiencies I mentioned in the following video lectures can already be outdated in a few months after the recording of this video lecture. I will do my best to keep the following lectures up to date. The current version is of February 2023. In addition, I only report conversion efficiencies that have been certified by external institutes. Let's consider the crystalline silicon PV technology. The back surface field conversion efficiencies are in the order of 20% and the PERC is in the order of 25.0%. Fraunhofer ISE has demonstrated record efficiencies for the TOPCon concepts, a 25.8% using N-type wafers and 26.0% for using P-type wafers. LONGi has demonstrated the current record efficiency for heterojunction solar cells, 26.3% for monofacial front contacted cell and 26.81% for the interdigitated back contacted cell. This is the current world record for crystalline silicon based single junction solar cells. If you focus on the most important thin film PV technologies, we see that the record stabilized efficiency for the thin film silicon PV equals 14%. This PV cell is based on an amorphous nanocrystalline triple junction processed at AIST in Japan with a lab cell device area of 1 square centimeter. Solar Frontier, the leading CIGS module manufacturer, has set the world record for the CIGS PV devices to 23.35% with a lab cell having an area of around 1 square centimeters. First Solar, the leading cadmium telluride manufacturer, is responsible for the world record for thin film cadmium telluride PV technology, which equals 22.1%. If we consider the 3,5 technology, we see that under concentration, the 4-junction based on gallium indium phosphide, gallium arsenide, gallium indium arsenide and gallium indium arsenide 4-junction bonded device architecture has resulted in the highest efficiency reported for any PV device in the world, which is 47.6%. This was accomplished by collaboration between Soitec, CEA and Fraunhofer ISEN. Note that Alta Devices has achieved a record conversion efficiency of 29.1% for a thin film single junction gallium arsenide PV cell of about 1 square centimeter. Boeing Spectrolab has demonstrated a 5-junction bonded cell with an efficiency of 30.8% on the 1000 watts per square meter standard test conditions. Certified efficiencies for single junction organic solar cell is currently 15.2% and not shown here, and that's achieved by Fraunhofer ISEN. The perovskite solar cells have seen a rapid increase up to an efficiency of 20.7% in the last decade. Note that the device area of this record efficiency is relatively small. It is smaller than 0.1 square centimeters. The crystalline silicon PV technology dominates the commercial PV market. However, the record efficiencies shown here start to approach the theoretical limit of the conversion efficiency for crystalline silicon solar cell that equals 29.4%. For that reason, new hybrid multi-junction concepts are being developed with crystalline silicon as bottom cell. One architecture under study is a tandem cell with a high bandgap perovskite based top cell and a crystalline silicon bottom cell. The current record conversion efficiency has been achieved by Helmholtz and Q cells with a conversion efficiency of 32.5% for a 2-terminal architecture, which is higher than the 29.4% theoretical limit of single junction crystalline silicon cell. Another approach is the combination of the 3,5 semiconductors with a crystalline silicon solar cell. The record conversion efficiency is based on a triple junction cell with a 35.9% as processed at Fraunhofer ISEN. An important note is that the efficiencies of the emerging PV technology like organic PV and perovskite PV are not corresponding to stabilized efficiency. The performance of these cells still suffer from degradation. And here we touch upon a weak point of the NREL efficiency chart. It is basically comparing apples and oranges. Some of the record efficiencies are stable efficiencies and some efficiencies are not stable. Furthermore, some of the efficiencies are reported for very small lab scale devices with a size of only 0.1 square centimeters, and some are reported for large 6-inch wafer sized solar cells corresponding to an area of 250 square centimeters. This is at least 3 orders of magnitude scale difference between the lab cell and the wafer cell. Therefore, I prefer to present the record efficiencies per technologies as a function of the device size. I will do that in the next video lecture. So see you in the next video lecture.